Hello AP Statistics students. In this video we are going to take a look at one rule for the binomial distribution that we can sort of fudge a little bit. It's that independence rule. All right? There are certain situations where we can sort of bend the rules for that independence condition in order to use a binomial distribution. It's called the 10% rule. So, short story. We can fudge this independence issue only if it's because of replacement when a sample is less than 10% of a population. Okay, now, all right, I'm with you. You may not be with me on that, but let's take a look at an example. I think I can make that pretty clear. So, two of them here. Mr. Bolt's 8th period has 25 students, and we know that 6 of them have A's. Suppose we choose 5 students at random and see if they have an A or not. Can we use the binomial distribution to model this? So we got to check bins. So is it binary? Yes. You either have an A or you don't have an A. So a success is an A failure is not an A. Is it independent? Well, no, it's not. It fails this because if I choose a student that has an A, one of those 6, there's only 6 of them in this class of 25. If my first kid is an A, well, the probability that the next kid has an A is different. The probability that the first kid has an A is 6 out of 25. If that kid is picked, well, for the next pick, well, now the chances of getting an A are only 5 out of 24. That changed the probability on us here. So that actually kind of fails 2 issues. No, it's not independent, and it's not the same probability. Yes, n is fine. N is equal to 5. I'm choosing 5 kids. Same probability? No. The probability is changing for each one because of that independence issue. Now, can we fudge it though? All right, the rule says we're allowed to fudge this issue right here if our sample is less than 10%. So my sample is n equals 5. The population here is my 25 students. 5 out of 25. Is that less than 10%? Sadly, that's not right. 5 divided by 25 is 20%. Oh, well then the rule doesn't apply here. We can't fudge anything. The 10% rule fails. So no, we cannot use the binomial. No, we cannot use the binomial distribution to model this. The trials are not independent, and our sample is more than 10% of the population. All right, so here's a good example of when that rule cannot be broken. Okay? We cannot use the binomial distribution here. All right, now what if I make my population bigger? Now suppose we choose 5 students at random from all of Edison. There are 2,500 students at Edison. Suppose I rounded a little bit there, but stay with me. 2,500 students at Edison, and 1,000 of them have at least one A. Again, I'm making this up, but can we use the binomial distribution to model how many of the 5 will have at least one A? All right, so again, can we use the binomial? We check our bins. So is it binary? Yes. All right. If a student has an A, that is a success. If a student doesn't have an A, that is failure. Well, not failing. I mean, you get the picture. All right. Is it independent? No. This is also not independent, all right? If the first kid, so when I pick the first kid, the chances of them having an A are 1,000 out of 2,500. Okay? If they do have an A, all right, we pick one kid that has an A, the chances of the next kid having an A are 999 out of 2,499. All right, that's different. But I think you might see why it doesn't matter. Well, yes, it is different. Are these two fractions really that different? And when it comes down to it, no. They're so close that in this case, it's not going to make a difference, and we're going to be allowed to fudge this independence rule. But we'll get there. So let's keep doing bins. All right, independence, no, technically they're not. N, number. Yes, again, n is equal to 5. Same probability. Again, yet technically no, because the probability changed because they're not independent. But not all is lost. We can now look for that 10% rule, all right? Are these two fractions close enough that it doesn't really matter? Well, that is checking the 10% rule. So my samples are only 5, right? I'm only looking at 5 at a time out of the total population of 2,500. All right, what is 5 out of 2,500? So that is 0.002 as my proportion, which is 0.2%. That is much less than 10%. I'm only sampling 0.2% of my population. That tells me that I don't have to worry about replacement in this case. So that means that we can ignore the we don't ignore the independence, we ignore the replacement. So this, because we're only, but because we are only sampling 0.2% of the population, we can ignore the replacement issues and say we have independence. Okay, so essentially, same probability, yes. Okay, because we are sampling 0.2% of the population, which maybe I should add is much less than 10%, which is much less than 10%, we can ignore these replacement issues and say that yes, we do have independence. Now, is that going to be perfect? No, it won't be a perfect model, but it'll be pretty darn close. All right, if you want to see the difference here, I can show you the difference real quick. So the real probability, let's check one. Let's say probability that all 5 have an A. X equals 5. So this is the real probability here, where we see that the conditional probability is changing things. So what is the probability that all of these 5 random people that we pick have an A? Well, we got the first 2. Then the next kid, because I've taken out 2 that have A's, now there's only 998 with an A out of 2,498. And each of these just keep going down by 1. 1, 2, 3, 4, and 5, 996 over 2,496. That is the true probability. And so if I type that into my calculator really quick, give me just a quick second. All right, so I typed that into my calculator and I got 0.01017. So there's a 1% chance that if I pick 5 students randomly, they'll all have at least one A. All right, but what does the binomial say? All right, that's the actual probability. What does the binomial say? Now, we know the binomial is not going to be perfect because we're fudging this with this 10% rule, right? But what is it going to be? So the binomial says the probability that x is equal to 5. All right, so that is going to equal the binomial PDF. So I only want one probability. What is the probability that x is exactly 5? So n is going to be equal to 5. And the probability is going to be equal to, oh, I didn't say that, the first one. We're just going to go with 1,000 out of 2,500. All right, we're just going to stick with that single probability. And I want x equals to 5. So I'm going to type that into my calculator here. Where is it? Here we go. Got my 84 going finally again. So we are going to go second distribution. Find binomial PDF. Oh, I don't have the nifty. Oh, well, I can type it in that way. I'll have to do some checking there. Why isn't it giving me the nifty screen here? All right, yours is easier to type in then, but. Well, now it did it. What in the world? All right, so trials. 5 trials. P-value, 1,000 divided by 2,500. X value, 5. All right, paste that in, hit enter, and it gives me 0.01024. 0.01024. So take a look at the difference between those two numbers. Yes, they are slightly different, but not by any major amount. If I rounded these two, they are exactly the same. All right, you could say the 7 rounds the 1 up to a 2, so that is roughly equal to 0.0102, and that one is also 0.0102. It doesn't even round up. We're accurate to 4 decimal places. Okay, so we are allowed to sort of fudge that independence rule if the issue is replacement. All right, it's like, whoa, you're sampling without replacement. That's usually an issue. You can't sample without replacement because that changes the probability. But if you're taking away less than 10% of the population, it doesn't make a big enough difference to matter. Okay? So that's one way how we can sort of fudge the rules a little bit with the binomial and that independence issue.